Hello friends, today is lecture number 3 of SOM. In the first lecture we have done introduction to stress strain chapter 1, and then we have done in second lecture chapter number 2 axial loading and chapter 3 torsion. Now today we will do chapter number 4 and it is SFD and BMD. Okay, so in this we should know first the beams. See, it is very simple. If I talk about beam, we have this, it is called cantilever beam. Then we have simply supported beam. This is simply supported. And then we have continuous beam. This is simply supported beam. And this is continuous beam. Continuous beam. Clear? And if I talk about support reactions, here we have support reactions in x direction. Let us assume this is point A. So I have a support reaction in x, that is RAX, in y, that is RAY, and a moment M A, moment MA, right? And if I talk about this, this is hinged and this is fixed. So at fixed part we have, if this is A point, RAX, RAY, right? And on the roller support I have only one reaction, that is RBY. Clear? And similarly here also the same thing happens. Clear? Now if I talk about this point, here the deflection, the slope is 0 and deflection is 0, right? This is fixed part. So if I draw its deformation, here the slope theta is 0, so it will be what, something like this, and then it will start to bend due to some force F. Clear? Now the chapter name itself is SFD and BMD, shear force diagram and bending moment diagram. So if I talk about SFD and BMD, this is shear force. Let us assume shear force is W, the length, and similarly bending moment diagram along some length, right? This one mistake is there. This is load deformation, load versus length. This is shear force versus length, and then I'll draw bending moment versus length, right? Now see very carefully. If I'm moving down, if I am moving in downward direction, then we will calculate area, and area will give the change, which can be calculated using integration, right? And if I move in upward direction, then I will get slope, right? That is, if I want to calculate V from M, then what I'll do, I'll differentiate the M. So V is what? dm by, V is to be calculated dm by dt, or you can say dx, because here I've written x. So this is V, right? So I want to calculate V from M, I'll do the concept of slope, and slope means differentiation, right? Similarly, if I want to calculate W, if I want to calculate V, I'll use the slope of M. Similarly, if I want to calculate the W, then I'll calculate the slope of V. So what is W? W is dV by dx, and W, load, is in downward direction, so that's why I'm putting here negative sign. Clear? Because the load is in downward direction. Clear? And if I calculate the area of load versus length of the beam, area, then I'll get the value of shear force, right? Change in shear force. Clear? Like if I integrate W, if I integrate W with respect to x from some point A to B, then I will get what? I will get the value of V in the same limit A to B, right? So this is the meaning of integration, right? So if I calculate the area, or I integrate load versus length of the beam, I will get the shear force in that particular limit A to B, right? So this is very important point. Right, now let's move forward. Third, Now we should know the sign convention. Like if there is a beam and in this side, see very carefully, it is usual. Like in left hand side, if it is in clockwise direction, I'll take it positive. And usually just remember, we will do the calculation from left to right. Right, from left to right. So on left side, if it is clockwise, it is positive, and just opposite you will do on the right side. So in right side, if clockwise is positive in left side, so in right side the clockwise will be negative. That means what will be positive? Anti-clockwise, right? Similarly, if anti-clockwise is negative, if clockwise is positive, anti-clockwise will be negative, obviously, right? And on this side, on this side, opposite of this, that is, this is anti-clockwise, so here I'll do clockwise, so clockwise will be negative, right? And if I talk about the shear force, it is also as usual, like upward. If the force is applied in upward direction, it will be positive, and just do reciprocal. If upward is positive, here downward will be positive. Similarly, if upward is positive, so downward will be what? Downward will be negative. Simple. And if down is negative, so this side opposite up will be negative. Clear? So this is for shear force, SFD, shear force diagram, and this is for bending moment diagram. Right? Now I'll tell you one very important thing. In cantilever, bending moment, the second part, bending moment will be maximum at free end. Right? So you don't want to calculate, just remember this, bending moment will be maximum at fixed end. Right? Next, contraflexural point. Contraflexural point. What is contraflexural point? It is related to bending moment. The point at which the bending moment is zero, and changes its sign. Changes sign. So that point is called point of contraflexural. Right? Next, again, it is the point related to bending moment. Bending moment will be maximum. Where it will be maximum? Where shear force is zero and changes sign. Right? So if shear force becomes zero at any point, like for example, if I draw something like this is positive, this is negative, this is shear force diagram, Vx, right? So at this point, bending moment will be what? Will be maximum. Bending moment will be maximum, and this point states that if I draw bending moment versus length of the beam, and bending moment comes like this, for example, positive, negative, so this point is called point of contraflexural. Clear? Here the bending moment is zero, so that is the point of contraflexural. So all these 3 points are related to bending moment. And one more important point for uniform bending moment, if the bending moment is uniform, then for that part shear force is zero, right? So this point is also very important. You should directly remember this, right? Now I will tell you some maximum bending moments for 8 cases, right? So see, if I take a cantilever beam and I apply a load here, W, first case. Second case, I'll apply a moment, and then I will take a uniform loading condition. After that, I will take a triangle case, straight triangle, and then I will take a triangle in opposite side, right? So this is the distribution of load. So if I talk about this, the maximum bending moment, Mmax, will be what? WL. Here the maximum bending moment will be the moment itself, right? And here the maximum bending moment will be what? As we know, the net force will be at the centroid, so it will be what? WL, and this length is L by 2, so force into distance. So what I will get? WL square by 2. Similarly, here also the load will be at somewhat here, right? And this will be what? Half WL, and this length will be what? This is 2L by 3, this is L by 3. So just multiply them. Simple. So WL square by 6. Similarly here also, if I apply the load, resultant load, it will be this. The load will be what? Half WL, and the length will be 2L by 3, right? So 2 gets cancelled, so WL square by 3. Clear? So these are the 3 cases. These are the 1, 2, 3, 5 cases, right? Now I will tell you simply supported beam cases. It is very important. First, we have this. Let us assume a load W is applied here, W, and this length is A, this is B, and the total length is L. So it is very simple, W AB by L. This is the maximum bending moment. And if I talk about uniformly distributed load, this is uniformly distributed load, W, then it will be what? Yes, this is very important, WL cube by 8, right? WL cube by 8. And if I talk about its position, it will be at which place? And one more case you should know, that is simply supported beam only, but the load is non-uniform, linear non-uniform, triangular shape. So if I talk about its position, where will be the maximum bending moment? It will be L upon root 3. L upon root 3, right? And just write the equation of bending moment, you will get the value also. Clear? See, for example, just I am explaining you for this part, right? I'll derive maximum bending moment, right? So let us derive it. This is something like this, and this. So the very first step is calculate the resultant force, reaction forces you can say. So if I want to calculate the reaction force, it is very simple. Here I'll get 2 reactions, but only y direction reaction will be there, RA y, and this is RB y, right? And this resultant force will be something here. This is 2L by 3, and this is L by 3, and the force magnitude is half WL, right? So I'll write a moment equation at A. So moment of A is 0. So what I'll get? This is clockwise. So half WL into 2L by 3. This is NT. So minus RBY into the total length L. So what I'll get? This got cancelled out. So WL square by 3, right? And equal to RBY, and this L got cancelled out. So I'm getting this WL by 3, right? So RBY is WL by 3. And if I want to calculate RAX, you can apply the shortcut RAY. Sorry, RAY. So RAY I want to calculate. I'll write this into opposite length upon the total length. So this got cancelled. So what I'll get? RAY WL by 6. And see, if you add these two, 2 plus 1 3, 3 by 6, 2 WL by 2. So here also what I have? WL by 2, half WL by 2. So it is same only, right? So reactions we have calculated, just write them here. So this reaction was A, which I got WL by 6, and this is WL by 3. Now I want to write the moment equation. So moment equation, if I want to write, you can take from either side. Let us assume I'm taking this side, right? So just draw it separately. This is WL by 6, and the net force will be something here, right? So this is net force. Now what will be the force? Let us assume this is X, right? So if this is X, this length will be what? This is X, so this length will be what? L by 3. That means X by 3. And this force is what? This force will be half base X into W, right? Just write the moment about XX. What I'll get? WL by 6 into X, it is clockwise, and this is anti-clockwise, minus half XW into X by 3 is equal to this is mx, right? Now if I want to calculate at 0, at x equal to 0, the moment will be what? Moment will be 0. And if I want to calculate the moment at L, x equal to, just see one thing, I want to calculate moment, maximum moment at L by root 3. So right here L by root 3. So if I calculate it, mxx will be WL square by 6 root 3, and similarly here I'll get L into L square. So WL square by 3, because root 3 into root 3 is 3, 3 2s are 6, 6 3s are 18, right? So if I take the LCM, what I'll get? See what I'm doing, just 3 and 3 multiplication, root 3 and root 3 multiplication. So I'm getting 3WL square minus root 3WL square by 18 root 3. right? So see, one thing we have done, this will be not W. W is what? W is the intensity of triangular load, but this intensity at some section which is at X will be what? We don't know, right? So let us assume it is Y. So if it is Y, so I'll write here Y. Now I want Y in terms of X. So what I'll do, I'll just use the similarity of the triangles, right? Small triangle and bigger triangle. So what I'll write, Y by X equal to bigger triangle W by L. So I want Y will be what? WX by L. So I'll write here half X into WX by L. What I'll get? WX square by 2L, right? So this is the load for us. So I'll write here WX square by 2L, right? So if I'm going to solve this is okay, and this will be something different, right? Just I'm cutting it. We'll do the calculations again. See what I'm getting, mx. For this part I'll write mxx equal to x, on the place of x I write L by root 3. So what I'll get, WL square by 6 root 3 minus, and here the value is what? Value is going to be, this part I'm just writing here, WX cube by 6, right? WX cube by 3 to the 6L, 6L. Okay, now solve this. So what I'll get, L cube. So W L cube by root 3 cube, 3 root 3, 6 3 is 18. So 18 root 3. Now this is okay, right? So now just solve this equation. I'll get what? 3. So 3 minus 1 is 2. So 2WL cube, not L cube, L square. Yes, so this L cube is okay. Here we have L also, na? So this L got cancelled with this L square I'll get, right? Then only the subtraction could happen. So 2WL by 18 root 3. So this is the moment, maximum moment at L by root 3. I can write it here, 2WL by 18 root 3. So these are the 8 cases which we should know, right? In the similar way, you can write the equation for force also, shear force. Clear? So that's all for chapter number 4. Now we will do chapter 5 in the same continuation, because just we will do 2 chapters here, right? So chapter number 5, we have bending stress. It is very easy. Bending stress, like we have done shear stress. Shear stress we have done. Shear stress formula is what? Torsion. T by J is equal to G theta by L is equal to tau by R. In the same way, we are going to write the bending stress for bending moment, right? So very first point, we have a shaft which is cantilever, and we are applying a moment here, bending moment. M is called bending moment. So if I apply a bending moment, so now see very carefully, the bending moment is applied across Z, right? So as we know, this is X, this is Y, and this is Z. So if I apply bending moment along Z, so it will be going to bend, right? Along Z, Z is outside, so like this, so bending moment, or like this, bend, it will be going to bend, right? So if I want to write the equation of bending moment, I'll write M by I is equal to, M is the bending moment, M by I is equal to E by R is equal to sigma by Y, right? So what is R, what is Y? See, bending moment, just I have told you, along Z axis. In the similar way, the moment of inertia, this is also moment of inertia along Z axis, right? And if I talk about cantilever, it is going to bend like this, right? So after bending, it will be having what? It will be having a radius of curvature. This is called radius of curvature, right? And what is Y? Y is the distance from the neutral axis. If I draw its cross section like this, so this is Y, neutral axis, the distance from the neutral axis. If I draw its side view, I'll get something like this. So this is the point, and this is the distance Y. Clear? Y, R. E is the property, Young's modulus. Sigma is the stress at that fiber on which we are going to calculate, right? And if I observe this equation, you can see by the last one part, I can write I by Y. This is called Z, section modulus. Section modulus. And the section modulus tells us the strength of the beam. Strength of beam, right? And if I see sigma, shear stress, it is what? It is M by Z. That implies sigma is inversely proportional to Z. That means if the Z section modulus is very high, then the stress produced will be low, and that is the benefit, that is desirable, right? That is desirable, that we want, right? I want minimum shear stress in the beam. right? So now third point, and the Z only depends on cross section. It all depends on the cross section. It is not depending upon the force applied and any other quantity, right? And if I talk about a rectangular beam, a rectangular hollow beam, and I want to write moment of inertia about this axis, so I will be what? This is let us suppose this is A, this is B, and inside part is small a, small b. So what I'll write along the axis, AB cube by 12, and the inner part will be subtracted. So A B cube by 12. So this is the moment of inertia of the hollow rectangle, right? And hollow shaft, for hollow shaft I'll write moment of inertia is pi by 64 d4 minus small d4, right? So this is the moment of inertia of hollow shaft. Now if I talk about variable shear stress, variable shear stress distribution, variable shear stress distribution. So in this I am going to tell you three important cross sections. One is R, rectangle, circle, RCT, triangle, and then two more sections we are going to discuss, that is T section and I section, right? This is RCT. Now I want to write maximum shear stress. Now first of all, their representation. So this is the representation, shear stress representation, right? And for circular shaft, the shear stress representation will be for variable shear stress, right? This is variable shear stress. If the shear stress is uniform, then its distribution is how? I can draw it here. See? This is not shear, this is normal stress, right? So normal stress representation will be something like this. Maximum at the top fiber, minimum at the bottom, minimum at the center, and again maximum at the bottom. This is sigma max. And sigma max can be calculated by this formula. You can equate this and keeping y as r by 2 radius, right? Now coming on this, so shear stress distribution, shear stress is tau. So tau max, I want to write tau max, right? This is tau max at the center. Again for circular, the tau max is at center, but in triangle we are having tau max and tau neutral axis, right? Here I'll write tau max. Now see, it is very simple. If I want to write tau max here, 3 by 2 tau average, 3 by 2 3 2, right? After 3 2 I'll write 4 3 4 3 3 2, and after 3 we have 4 4 3 4 3 tau average, right? This is maximum. So take the maximum part. Which is maximum? This is 1.5 and this is, so this is maximum 3 by 2. So I'll write 3 by 2 tau average as maximum, and the leftover part here 4 by 3 tau average, tau about neutral axis. Okay, RCT, just learn this: rectangle, circle and triangle. Now if I want to draw the shear stress distribution here, what I'll get? See, the shear stress is parabolic, but when there is a drastic decrease in the cross section, the shear stress drastically increases, right? So here is the chance of failure. So this is the distribution graph. And for I section, again the same pattern you can observe. It was parabolic, but the cross section is changing, drastic increase, again parabolic, cross section is decreasing, drastic increase, and again parabolic, right? So that's all for chapter number 5. Now